For centuries, humanity has looked upward and tried to decode the sky, building mathematics, philosophy, and entire civilizations around the belief that the universe follows rules we can eventually understand. Stars were mapped, galaxies classified, and cosmic history reconstructed piece by piece like an enormous puzzle. Yet now, something has changed in that picture. Not slowly. Not gently. But in a way that forces even the strongest scientific frameworks to pause. Because what is coming from deep space observations is no longer behaving like a clean extension of known physics. The data coming from the James Webb Space Telescope is beginning to show tensions between expectation and reality, between models and measurements, between what should exist and what is actually being seen. And the deeper we look, the more those tensions multiply. Across multiple deep field observations, Webb has captured galaxies that appeared too developed for their age. Structures that seem too organized. Light patterns that show an unexpected level of symmetry. These are not single anomalies scattered across different datasets. They are repeating features appearing in different regions of the sky, as if the universe is echoing itself in subtle but measurable ways. In one region of space, a galaxy cluster reveals light points arranged with an unusual geometric precision. Instead of chaotic distribution shaped by gravity alone, the pattern suggests alignment that feels almost deliberate. Nearby observations show spiral galaxies with motion curves that deviate from predicted models, not slightly, but in ways that accumulate into a larger inconsistency. Individually, each deviation might be explained. Combined, they form a pattern that is harder to dismiss. Then comes one of the most debated discoveries: exoplanets that should not exist under current formation timelines. One such world is HIP 65426b, a massive gas giant orbiting far from its young star. According to standard planetary formation theory, a planet of this size should require a long-lived, dense protoplanetary disk to form. But the system around it is too young, too sparse, and too dynamically incomplete. There simply isn't enough time or material in the conventional model to account for what is being observed. Yet the planet is there. Bright. Massive. Stable. Existing in a configuration that does not easily align with known planetary evolution pathways. This forces a difficult question. Are we missing a stage in planetary formation, or are we misunderstanding how planetary systems evolve under extreme conditions? In another observation, Webb detects an Einstein ring, a perfect gravitational lens where a foreground galaxy bends light from a more distant one into a near-complete circle. While gravitational lensing is well understood, this particular alignment approaches near-perfect symmetry. A full, uninterrupted ring of light. Mathematically precise in a way that feels almost artificial, not because physics allows perfection, but because the probability of such exact alignment across billions of light-years becomes extremely low. Not impossible, but rare enough to raise questions about whether our statistical expectations fully capture cosmic-scale behavior. Some scientists interpret this as coincidence amplified by scale. Others quietly note that repeated near-perfect alignments across different datasets begin to look less like randomness and more like a property of the underlying structure of spacetime itself. Then comes the most disruptive category of findings: early galaxies. Webb has detected fully formed, massive galaxies existing just a few 100 million years after the supposed beginning of the universe. These galaxies are not small protostructures. They are mature, structured systems with defined shapes, brightness levels, and mass distributions comparable to galaxies like the Milky Way. According to standard cosmological timelines, this should not be possible. There was not enough time for matter to cool, collapse, form stars, evolve structures, and stabilize into organized galaxies of that scale. And yet they exist. This forces a recalibration of assumptions. Either galaxy formation occurred far faster than models predict, or the early universe behaved in a way that current physics does not yet fully describe. Some cosmologists are beginning to suggest that the early universe may not have been uniform chaos, but instead contained regions of accelerated structure formation, zones where physical constants or initial conditions allowed matter to organize far more rapidly than elsewhere. This remains theoretical, but the data continues to accumulate. Even more puzzling is what appears in seemingly empty regions of space. Webb detects gravitational lensing where no visible mass is present. Light from distant galaxies bends as if passing through something massive, yet telescopes detect no stars, no gas clouds, no black holes. Only distortion. Only gravity. This is typically attributed to dark matter, an invisible form of mass that does not emit light but exerts gravitational influence. However, in some cases the lensing patterns appear unusually structured, with sharper boundaries and more defined curvature than expected from diffuse dark matter distributions. Instead of a cloud, it behaves like a shaped region of influence. A region that seems organized. This raises speculative but carefully discussed possibilities. Is dark matter truly uniform and particle-based, or could it form structures on scales and configurations we have not yet modeled correctly? Another discovery pushes the conversation further: the cosmic web itself. Webb has mapped intergalactic filaments stretching across billions of light-years, forming the large-scale structure of the universe. These filaments connect galaxies like threads in an enormous cosmic network. But in certain regions, the arrangement appears unusually regular. Galaxies are not just connected, they are spaced in repeating intervals. Voids appear in structured patterns. Density fluctuations show rhythmic spacing. While standard cosmology explains this as gravitational evolution over time, some researchers note that the regularity resembles patterns found in systems with underlying organizing principles. Not design, but structure. And structure always invites interpretation. Then comes a more controversial line of inquiry: whether dark matter could carry information. Not information in a technological sense, but in a physical memory sense, where gravitational configurations persist and influence future structure formation. If true, this would imply that the universe does not reset between epochs, but instead evolves with a kind of structural continuity. In this view, galaxy clusters might not form independently each time, but could be influenced by residual gravitational patterns from earlier cosmic configurations. It is a hypothesis at the edge of modern physics. But it is being discussed because some large-scale distributions appear to echo earlier structural patterns in subtle statistical ways. And then there are the signals. During deep field scans of apparently empty regions of space, Webb has recorded faint, periodic fluctuations in light intensity. These signals do not match known astrophysical sources such as pulsars, quasars, or background radiation noise. They repeat with precision. Then stop. Then resume. Always consistent in timing, always emerging from regions with no detectable luminous source. Initial explanations point to instrumentation artifacts or processing interference. But repeated detections across independent observations make that explanation increasingly difficult to maintain without additional evidence. At present, no confirmed astrophysical origin has been identified. This leaves the signals in a category scientists are cautious about: unexplained but real. Not interpreted. Not classified. Simply observed. And this is where the true shift occurs, not in any single discovery, but in the accumulation of them. Galaxies forming too early. Planets existing outside expected timelines. Gravitational lenses appearing in empty space. Large-scale structures showing unexpected regularity. Faint repeating signals without clear origin. Each one individually sits within the edge of uncertainty. Together, they begin to challenge the boundaries of current cosmological understanding. The universe is still not understood as chaotic or random. Physics still holds. Gravity still works. Light still behaves consistently. But layered onto that familiar structure are patterns that are not yet fully explained. And this is what makes the current moment unusual. Not that science is breaking, but that it is expanding under pressure from data that does not yet fit cleanly into existing models. The deeper implication is not that the universe is wrong, but that our interpretation of it may still be incomplete. And so the question shifts. Not from, what is out there, but to something more uncomfortable. How much of what we see is truly unexpected, and how much is simply unmodeled complexity waiting for explanation? For now, there are no final answers. Only increasingly precise observations. Only expanding questions. And a growing realization that the universe is still far from fully written in the language we currently understand.